Let's talk about diamonds today. While I'm getting the basics covered, I will show some photos I took of either samples I have tried or the diamonds I use in the stones and emulsions I make. This is much of what I do for a living, so please follow the link in the video description to learn more or purchase any of the sharpening products I make. So, what are the variations in diamond powders that are available, and how do they apply to knife sharpening? The three types of diamonds are monocrystalline, polycrystalline, and resin bond. Polycrystalline diamonds are made so they will fracture, exposing fresh sharp edges when exposed to enough pressure. As far as I can tell or have been advised by my suppliers, they have no use in knife sharpening. You don't want your diamond crystals breaking down when bonded in a stone, and when used on a strop, they won't see enough pressure to fracture. They also cost much more than monocrystalline diamonds. More on the other two later. When picking a diamond powder, you can choose the type of feedstock, the shape of the crystals, and how well it is sized. The feedstock refers to both the quality of the synthetic diamonds as well as the characteristics of it. Do you want a tough crystal or one that is more wear resistant? The tough crystal will hold up better, but the sharp edges will round quicker. The harder crystal will wear much longer, but it is more brittle if exposed to too much load. The shape of the crystals is important, and generally the highest quality is the closest to round. Often I see photos of nice, nearly round crystals with even-sized facets when someone is talking about metal bond monocrystalline diamonds. This is optimal, but I doubt anyone is making stones from this quality of diamond for sharpening knives. A perfect crystal would have an aspect ratio of 1.0. The crystals in the photo are what I use and have an average aspect ratio of 1.3. How well sized the powder is affects not just the few stray crystals that are much larger than the mean, but mostly how much powder is well under the mean size. The fines don't do much good and take up a lot of space that should be filled with even-sized crystals. With resin bond stones, the aspect ratio isn't as important as the sizing and the quality of the feedstock. Another variable is friability. This is how easy it is to break the abrasive down. Polycrystalline diamond is a friable and monocrystalline is not. Friability is also an important variable in aluminum oxide and silicon carbide powders as well. I don't know about the friability options for polycrystalline diamonds, but there are several options available for the resin bond diamonds I have in this photo. The resin bond crystals are the charcoal gray ones, and the clear to light yellow ones are monocrystalline diamonds. They are both 160 microns, so a pretty good comparison of the two types. These resin bond crystals are a lower friability and blockier crystal for this type of diamond. I made some test stones from this diamond in 80 and 160 microns and found they didn't cut nearly as well as the monocrystalline diamonds. When I added more diamonds to the mix, it still didn't cut very well and the stone wore quickly. These crystals just didn't have the same sharp edges as the monocrystalline crystals do, and honestly, nothing else does. Here's another option, nickel coating. I think this is with a 40 or 50% nickel content. This coating is to increase the adhesion to the bond. It provides both a larger area to bond to, but also a lower energy surface. Diamond is a very high energy material which makes it hard to bond to. Think of water beating on a freshly waxed car. The wax surface is high energy and repels the water. Diamonds do this too when trying to bond to them, even with nickel. I made stones from these diamonds, which are monocrystalline, in 80 and 160 microns also. They worked about as well as the resin bond stones in both diamond loadings. The reason the photos are all blurry is the focal length with this microscope is about 2/1000ths of an inch, and these crystals are 6/1000ths of an inch in diameter, being 160 microns. You can see this same problem in this photo, which is of the monocrystalline diamonds I use in my 160 micron stones and the 80 grit matrix stones. They have very pronounced cutting edges, so cut quite efficiently. These next photos are of the loose diamond I use on a glass slide. The first three are the 80 micron. And mainly just notice the consistency and size. It's the big deal with what I'm using. And then here is the 40 micron, and it's where I dropped the glass slide, and there's just a little bit left on it, but only having a few crystals makes it a little easier to see them. Again, of course, notice the consistency and size. Then here I've added a little more, pushed it around, and then I added a bit of diamond back to the slide so I could get more in the photo, but I don't think it really helps seeing it. But it does show the consistency and the size. You don't see any fines in these photos. And then here is the 20 micron diamond. And below that, it gets hard to see it with my microscope. Although, in hindsight, I probably should have tried. These next photos are all of the matrix stones, showing the diamond in the stones themselves. This is the 160 micron or the 80 grit matrix stone, and this is actually the side of the stone since I didn't have any that were undressed. Now, I put a little mineral oil on it to help make the resin translucent, although the oil does not soak into the resin. And being the side of the stone, interesting point here is you can see how the diamond crystals are quite evenly distributed, because the top of the photo is actually the bottom of the stone, and it's not, this is the one stone I'm most worried about the diamond settling while the resin is curing, and thankfully I'm not seeing any of that here, so I'm happy to point that out. Here's the bottom of that same 80 grit stone with that's dressed, actually used. You can see some dark spots from the metal. And again, I put a little mineral oil on it to make it a lot more viewable. But you can see quite a few diamonds are exposed and quite a few in the matrix. Then here's a photo of the 80 micron stone, or a 250 matrix. You can see put a lot of diamond in there. Yes, there's room for more, but it really doesn't help much, and it does increase the wear quite a bit. And then here's the 450 matrix, or 40 micron diamond. And from the 250 on, I use the same amount of diamond by weight. So it actually, you get a lot more cutting edges for the finer the grit gets. And finally, this is the 20 micron or a 950 matrix. And the diamonds are starting to look pretty packed in there. And now we get to a 1700 matrix, or the 10 micron diamonds. And if you look really hard, you can kind of see the individual crystals. And now for some bonus photos. This one is the sample I made with the nickel-coated diamond. And I, in hindsight, should have used the mineral oil. It'd look a lot better, but here you can see how the diamond crystals get exposed. The nickel wears off quickly. But you can see like pockets of nickel in here too, where the crystal got pulled out. Then these last photos are of the 80 grit Venev. I put oil on this, and word of note, you probably don't want to use oil on your Venevs unless you're going to just stick with it. Because the whole time I was taking photos, I was seeing little bubbles popping as the oil was soaking in. And oil doesn't come out too easily on these stones. But you can see, not sure what the black is. You can see the gold is the metal bond monocrystalline diamonds. I swear I've seen gray diamond crystals in Venevs before, so it makes me think they use a mix of different diamonds with some resin bond. Anyway, hope you enjoyed today's video. Stay tuned for more, and please go to my website if you're interested in any of the sharpening stones or products I make. Thank you.